Good afternoon, everybody. Welcome back after lunch. So I'm going to talk about stellar feedback and H2 regions. You've heard a lot about that already in the past few days, so I'll try to refer to things that you've learned already in the previous lectures. But before I do that, and that would be great. Before I do that, I don't want you to fall asleep during this lecture, so I would like to ask you to participate, try and keep you awake. So please scan this QR code. I will ask you a couple of questions during the lecture. I'll show it again, but first questions to see that it works for everybody and to count how many of you actually have watched The Office. What kind of bear is best? I'll give you just a few seconds so that you all connect. I hope everybody can connect, that there are not too many participants. If not, team up with your neighbor. That's not a problem. Okay. So I'm still waiting for a couple of people to vote. You don't need to think. Huh? It's not a trick question. All right. This is Jim, but dressed up as Dwight. That's from The Office. Okay, more people are connecting, more people are answering. I'm still always missing like 5 people, but it's converging. So I'll stop it. You can still connect later on. I'll ask more questions. I'm closing the poll now. If you don't have a phone, if you're not connected, these are the results. So I think the real answer is black bear. So well done for those of you who found it. I like the polar bear and the panda bear, so that's great too. Thank you. All right. Now, let's go to some real questions. So this is the outline of the talk. I'll talk about feedback. Is it important? Otherwise, we can just stop here. What are the main stellar feedback mechanisms and where are they important? This is basically what I'm going to talk about. But to start with, I'd like to ask you what you already think about feedback, if you think that's important, first for star formation. So for those of you who are not connected, these are the propositions, so you can also think about what you would answer. Stellar feedback has no impact on star formation. It accelerates star formation. It suppresses star formation, or it depends. With respect to no feedback. Yeah. All right. Just 5 more seconds. It's okay. There is no grade. Okay, I'll stop here. So it depends. It's apparently by far what got the most vote. We'll see then during the lecture and we'll revisit that at the end. Now, the other questions I wanted to ask you is that, do you think that feedback affects galaxy evolution? Because we're talking here about stellar feedback, so feedback from stars, individual stars, maybe groups of stars. Can that have an effect on the entire galaxy and on galaxy evolution at large? Okay. 2 seconds. Okay. Well, okay, I think that's pretty unanimous, and this is a great news. If some of you are working on galaxy evolution or are cosmologists, pay attention. It seems that it is important. Okay. Great. So before I go really into the importance of feedback, I just wanted to illustrate my talk, and I typed star formation on Google image, and I got this. And I want to say these are really pretty images, but this is not star formation. This is really all feedback. Every images that you can see that are these beautiful images here show the influence of feedback. Right? You see the hot gas and dust, you see the gas being pushed away here, forming these shells and these bubbles. So yeah, feedback is important, if for nothing else, at least for providing us with these beautiful images. Otherwise, all we would see would basically be the stars, right? And the gas that we see is actually the gas that is heated by the stars in these images. So feedback is important in the broader context, I think, of the matter cycle in galaxies, where the cold gas accrete on the galaxies in the diffuse interstellar medium. Under the effect of gravity, clouds form. And within these clouds, stars will form. And the effect of feedback is really to disrupt these molecular clouds, to push back the gas into the in a diffuse interstellar medium. And this is very important because the only other mechanisms that really could counteract gravity would be dynamical cloud dispersal. And I'm not going to talk about that today, but it cannot disrupt bound dense clouds, for example. So the only thing that counteracts gravity, that prevents all of the matter in the universe to collapse and form a massive black hole, is feedback. And then the collective effect of feedback will push gas out of the galaxy in the form of galactic winds. I'll touch about that just a little bit toward the end, if I have time. So this is very important that we have these stellar feedback mechanisms, because as I was saying, other mechanisms can't sustain or can't counteract gravity. So turbulence that we know exists in the interstellar medium dissipates quickly and heat the gas. And what I mean by quickly is in one dynamical time. So that would be 1 over omega in the galaxy, and that would be just maybe a few tenths of million years, so if you just had no mechanism to sustain this turbulence. Once turbulence has dissipated and heated the gas is actually going to cool pretty quickly again, a few hundreds of megayears down to about 1 megayear down to a factor of 100, smaller than that in the cold neutral medium. So without feedback, really the diffuse ISM would just collapse into dense clouds. All of these clouds would collapse and form stars. So the reason that we're not sitting in a black hole is really feedback, where the young stars inject energy and momentum in the gas and can revert or limit the collapse. And this is the phenomenon that is known as self-regulation, which I'll discuss later on. A few notes about that. Turbulence dissipates quickly, I said, but it's not unimportant because it creates structure in the ISM. You've seen that already. It creates filaments, sheets, really structure. It structured the gas, which means that stars are born in a clustered environment. And this is very important for feedback, as we'll see later. Massive stars are the most important feedback sources, as we will see, but they also live the shortest, which means that this regulation by stellar feedback is fast. And these two phenomena combined mean that the effect of feedback are correlated both in time and in space. Okay. So I'll go really to the meat of this talk. Let's go through the different stellar feedback mechanisms. And for that, I'd like you to suggest, either by raising your hand, that's totally fine, or if you're afraid of saying a big mistake or something really wrong, type in the chat. I think we should be able to see the chat here. Maybe. Has somebody typed something? Maybe here. Yes, AGN. Okay, what else? Supernovae, yeah. So I already, spoiler, I'm not going to talk about AGN here. I'm going to focus on stellar feedback. If you see an answer that is already there, you can also upvote it. So jets, photoionizations again, supernovae. Oh, well, this one is very complete. Thank you. Supernovae, winds, cosmic rays, radiation, UV, radiation from stars. Okay, great. I think we pretty much got everything. That was just to help you. This is the image that was published by NASA just a few weeks ago, I think, for the first anniversary of the James Webb telescopes. And you see here many different kinds of feedback. You see the jets, so we've mentioned that. You see these shells here that are produced by the by the winds that are ejected by this massive star here in the middle. You see the gas being heated and ionized. So here is a list of some feedback, some of the most important feedback mechanisms, and I think we've mentioned all of them. So outflows, they mostly disperse the natal cores of individual stars, not the big molecular clouds, as we will see. Radiation, so non-ionizing radiation or ionizing radiation that heats the gas or that ionizes and photoevaporates the gas. Stellar winds, creating hot bubbles. Radiation pressure, so that I haven't seen that one, I think, in your answers. Sorry if I missed it. Supernovae, of course, and cosmic rays, which I won't have time to talk about today. So I'd like to go in the next few minutes, for the first part of this talk, basically, to go through each of them, look at what they do to the surrounding medium, and try to see how fast they act. So what are their characteristic timescales? So I'll try to do that for most of them, not all of them. I'll explain why. And then in the second part of the talk, we'll see how we can use these timescales, these characteristic timescales, to see how we can constrain observationally the importance of these mechanisms. Okay, so let's start with outflows. So accreting systems, which with rotation and a magnetic field, tend to exhibit bipolar outflows or collimated jets. And you can see that, I think if you have a trained eye, you can see that in its image. I personally find it quite difficult. So these molecular jets are seen with H2 here, molecular hydrogens. So they're in red. And you see, yeah, these sort of filaments in red here and there. It's not really easy, I find, to see these outflows. But then if you overlap CO and you actually represent CO with the red shifted component and the blue shifted component, there you can really see these outflows. So you see here like the blue component and the red component. So here is an outflow, here as well, like a very big one here. You have another one here perpendicular, and you have another one here that is less collimated. This one is quite collimated. This one is more like a bubble or so. So they're visible in really different shapes, but so all of these are outflows from young stars. They have different speeds, so from a few kilometers per second to over 1,000 kilometers per second. These outflows generate turbulence. I've said it, they blow out the parent cores. They can limit the collapse of the cold gas on the star, but generally they cannot halt star formation. There is not enough energy there to stop completely star formation in a giant molecular cloud. If you're interested about outflows, I really encourage you to read the review by John Balley in 2016. It's really complete and really detailed and very interesting. Outflows are also can also be simulated. It's quite challenging actually to simulate outflows because they happen on very small scales. So you need very high spatial resolution, and they're very fast. So you also need very high temporal resolution. And you need these high resolutions on large scales because you also need to consider the large scale accretion from the large scales on the stars, which act on larger scales and larger time scales as well. So it's quite challenging and it's quite computationally demanding to do that. I maybe just wanted to run it again. So you can see here the gas collapsing, and here you can see the ejecta from the young stars forming this cavity. So really entraining the gas from the surrounding of the stars with this expansion here, this bow shock here, expanding and being ejected by the outflow. Now, next mechanisms, the non-ionizing radiation. So non-ionizing photons that are below 13.6 electron volts, so they don't ionize hydrogen. So local UV photons from the massive stars mainly, so OB stars, can be absorbed mostly by small dust grains and generate photoelectric heating. You've heard a lot about that already with Benjamin's talk on last week, but even Julia's talk this morning. And this photoelectric heating is actually very important. It's mostly important in the diffuse gas, but it's important for the thermal balance and the chemistry in the warm neutral medium and the cold neutral medium. In addition to this heating, you also have a momentum component. When photons are absorbed by gas or by dust, they transmit momentum. And I'll talk about that later on when I'll talk about radiation pressure. But first, what happens with the photons that are more energetic? So above 13.6 electron volts. They will ionize the medium, the nearby gas. So for a fully sampled IMF, you can have an ionizing rate with like this, so proportional to the stellar mass that you're forming. You can consider that you can have a fully sampled IMF if you have a mass of typically above 100 solar masses, something like that you're forming. And so let's imagine, very ideal case, you have this cloud of gas with a constant density or homogeneous density. It's not very realistic, okay, but it's a simple case. You form some stars in the center. They're going to ionize, they're going to send photons with an ionizing rate, Qi. These photons will start ionizing the gas. So at the beginning, you have the density in this bubble here that is equal to the original density. So the density of ion is equal to the density of electrons is equal to n. And you have an ionizing front, right? So the further the photons propagate, the further the ionization front. But at the same time that these photons are ionizing progressively more and more gas, some of the hydrogen gas, some of the ionized gas here is some of these ionized hydrogen atom will recombine. So basically what you do is that you consume photons to ionize hydrogen, but then this hydrogen will recombine. And then you have to reionize this hydrogen atom again, right? And this recombination rate is equal to alpha B, or we call it alpha B. So basically what you're going to have at some point is that the recombination rate will equate the, or every photons that is emitted by the source will be consumed by this reionization, by this recombination rate. So at some point you will reach a balance between ionization and recombination, which sets then what we call the Strömgren radius, right? So this is the volume of this bubble here, that's ionized bubble. When this volume times the density of electron, the density of ion times this recombination rate is equal to the ionization rate. When you have this, then you stop expanding your ionization front. So you stop here at this Strömgren radius. But this is not all, because while doing that, you have heated the gas in that ionized bubble to temperatures of about 10 to the 4 Kelvin. but the medium around it is 10 to 100 Kelvin, right? It's just cold neutral gas. So what happens is that this bubble here is highly over-pressurized, so it will expand. And so you have this expansion of the hot bubble in the cold neutral medium with accelerations of a few tens of kilometers per second. You can actually, this has been calculated. So this equation here of motion of the swept up shells, this is the quite famous solution from Spitzer in 1978. So it's basically yes, just solving the equation of motions with the mass of the swept up shell here, and on the other side, the pressure of the H2 region. So you can solve this equation to get the radius expansion of the ionization front. And what I'm interested in, I said, was to get the timescales. And again, I'm placing myself here in a very ideal case where I have a spherical cloud with homogeneous density. At the center of this cloud, I'm forming a stellar source. And I'm going to look when this ionization front reaches the size of the cloud. And then obviously it stops, right? I don't have a cloud to, well, it doesn't stop, but my cloud is destroyed. So I don't have a cloud to destroy anymore. So basically, I'm just solving this equation here for the ionization front radius equate the GMC radius. And this gives me a characteristic time for the photoionization to destroy my GMC, okay? So it depends on the Strömgren sphere. So basically it depends on the luminosity of the internal source and the density of the medium. I didn't mention that. Oops, there. Here. This Strömgren sphere radius here depends on QI and on the density of the medium. All right. Oops. Okay. Next, sorry. Next mechanisms is stellar winds. This is going to be really mostly important for, again, for massive stars. For OB stars, you need to reach a certain temperature, so quite high temperature, a few times 10 to the 4 Kelvin, to actually launch these powerful winds. So this is only the case for massive stars. They will create a shock, so they will shock the surrounding gas and create a high temperature bubble. So something above 10 to the 6 Kelvin. And this is what you see in that image here. So this is a region in the LMC, 30 Doradus. And the blue that you see here are X-rays observed by Chandra. So this is really tracing the very hot gas. And you see these bubbles here that have been created by the winds of massive stars. Again, there is a very nice review by Smith in 2014 that is focusing more on stellar winds. So I encourage you to have a look, read it if you want to know more. Observationally, it's actually quite debated or not so easy to actually see the effect of the winds. And this is an image in Orion, so the C2 emission line. And they have measured the velocity or the expansion of these bubbles here, these 3 bubbles here that you see in Orion, to see if they were actually created by winds or if it was just thermal expansion. And for 2 of these bubbles, they have relatively low shell expansion. So these plots here are showing the position velocity. So just along a slice here along the across the bubble. So these 2 shells are expanding relatively slowly, and this is compatible with just thermal expansion. This last one that is expanded at 13 kilometers per second could be driven by winds. There are arguments for, arguments against. So this is not so clear yet. The reason, oh, sorry, before I go, I go there, let's stay for a minute more on the very simple case. So again, let's look at the timescale. How fast can actually this wind destroy or push away the gas from an entire GMC? So the injection rate, the energy injection rate from the winds per stellar mass is something like that. So 1/2 of the mass that is ejected times the velocity square of the wind. Then again, we have this quite famous solution from Weaver et al. in 1977. So again, considering a very simple case, homogeneous density, a source at the center of a cloud. And so you can actually solve, again, the momentum equation to find the radius evolution of the shock. And it's going to be something like that. It's going to depend, again, of the luminosity of the source that is in the middle. It's going to depend on the volume density of the cloud. And again, we can solve this radius evolution of the shock to say, okay, when does that shock reaches the cloud radius? And at this point, I can consider that my cloud is gone. And this gives me this characteristic timescale here. The coefficients are not important, but again, it depends on the luminosity of the source and on the density. But this was for a very simple case. In reality, you don't have this smooth interface between the shock and the rest of the medium, but you have a turbulent medium. So actually, the previous image that I showed here looks like something like this, where you have a very complicated interface. You have a medium that is not at all homogeneous in density, but that has a structure. You have turbulent mixing, et cetera, and this turbulent mixing makes the cooling much more efficient at the interface here between the shock and the medium. So as a result, the radius expansion is going to look like something like this. So a little bit different from before. That means that the characteristic timescale is going to be a little bit different. And because it's not necessarily easy to compare these two mathematical expressions, here is a plot that does that for you. So this is the radius as a function of the radius of this shock here as a function of time. The dashed lines are for the pressure-driven, so the Weaver solution from the previous slide. And the solid line is from this paper here from Lancaster et al. In 2021. And so these are for different stellar masses. But let's just look at this, at the most massive one here. So you can see that if you take the very idealized solution, and here we're considering a cloud of 20 parsecs, you destroy your cloud in about, 0.2 million years, right? So it's really fast. It's very efficient mechanisms. Now, with this structure, if you're in a little bit less idealized case, actually you don't go that fast. The expansion here is much slower, and you only destroy your cloud in almost 1 megayear, so about a factor of 5 slower. So this is quite important to take into account, right? To know whether stellar winds are an important feedback mechanisms for to stop star formation or not. So this was analytical solutions, but the same team has also done simulations to show that. And you can see here that indeed the temperature really drops at this interface, this very complicated, like fractal interface. You have a drop in temperature, so efficient cooling. The cooling rate is very important at all of this interface. And the fact that it's fractal, then you have much more, you can cool much more efficiently than if you had just had a simple spherical interface. Now, the next mechanism is radiation pressure. So I've mentioned that already very quickly about the non-ionizing radiation. So when you have photons being absorbed or scattered by gas or dust, you have transfer of energy, so creating heating, and you have transfer of momentum with this expression for the momentum of a photon of frequency nu here. You have two ways that you can transmit momentum, either directly, so if you have direct absorption and scattering of the photons by dust or gas, or you can have indirect absorption. So a photon will first be absorbed by dust, be re-emitted, typically in the infrared, and this is a new photon that can again be absorbed by dust and again transmit momentum and apply radiation pressure. So we can do a small estimate here. So for point source of luminosity L, you have, so the radiation pressure can be expressed like this. So with the luminosity here and basically the sphere, again, we're in this ideal case, right, where you have this interface here. There is, we typically add this coefficient here because the photons are not necessarily, all the photons are not necessarily absorbed immediately by gas or dust, right? You have to consider whether the medium is optically thin or optically thick. So you have this additional coefficient that was introduced here by Krumholz and Matzner to give you how much of this momentum is actually absorbed by the gas. And this can be lower than 1, right? It suggests that it's a fraction. If you have a totally optically thin medium, it can even be 0. So it doesn't matter how high the source is. If the medium is optically thin, the photons can just travel through the medium, right? But if the medium is optically thick, even moderately optically thick, you have absorptions of these photons, and you can have multiple absorptions and re-emission. So it means that this coefficient can also be higher than 1. These mechanisms of radiation pressure is significant only for massive stars. It's mostly significant for small regions with high opacity because of this trapping function, right? If your medium is not optically thick enough, the photons can just escape and they won't exert a pressure on the surrounding medium. There is debate, a little bit of debate as to whether this mechanism is really important or not, that whether the momentum transfer is important or not. But I think there is a good agreement that the radiation pressure typically cannot halt star formation. You can, again, do the same estimate for the timescales. So we have this force here that is proportional to the bolometric luminosity of the source. And we have, again, this, it's kind of this trapping factor here, where we have, here we express this as 1 plus the optical, the infrared optical depth. What is this infrared optical depth for a typical GMC? Well, if you do the calculation and plugged in the right units, you have something like that for typical GMC with tau IR is something like a few 10 to the minus 5, 10 to the minus 4 maybe. This is much lower than 1. So typically, GMCs will be optically thin to infrared radiation. So UV photons can be absorbed by dust, well, will be absorbed by dust. But once you have interacted once with the dust, you can emit these hot dust grains will emit infrared photons, and these infrared photons will not be reabsorbed again mostly. This is what it means. Again, you can solve this, so the momentum equation putting in this radiation pressure force for constant volume density GMC. So basically, again, calculating at what point do you consider that the cloud is gone if you apply this radiation pressure force. And this is going to give you something like that, so proportional to the density of the cloud. Okay, the last feedback mechanisms that I'm going to mention are the supernovae. So you probably know that they're the largest source of momentum injection in the ISM. So each supernova typically yields 10 to the 51 ergs, most of which will end up as thermal energy. It drives turbulence in the molecular clouds, but the efficiency really of supernovae in destroying molecular clouds will depend on the environment. So how dense the nearby gas is and how clusters the supernovae are. And this has been shown by multiple simulations. I'm showing here the example from this paper, Girichidis et al. In 2016. This is what happens. So this is showing the column density. So blue is low column density, red is high. This is if you put the supernovae at density peaks, right? So you have your medium with some structure and you make the supernovae explode where the gas is densest. This makes maybe a bit of sense because this is where the stars are formed, right? In the densest part of the clouds. Well, you see that the effect of these supernovae are quite limited. You reach maybe a little bit cyan, but not dark blue. Now, if you put the supernovae at random, completely random position within the simulation, you see that you do a little bit more. You clear up more the gas. You make bubbles that are a little bit more empty than in this first case. And now the third case here is that you make the supernovae to be clustered. So again, they're random. They're not necessarily at where the gas is the densest, but you make several supernovae explode at the same location. And then now you can actually really clear the gas, right? And this makes sense because basically what it says is that one supernova exploding in a very dense medium is not going to do much. If the medium is less dense, you can do more. But then if you add several, if you keep adding more energy to that same bubbles, then you can really start clearing the gas and have an effect on larger scales. The second important point about supernovae is that they actually have limited importance for halting the star formation. And this is because of their delay time. So when do actually supernovae explode? And how many of them explode? Because of the shape of the IMF, so basically you have more supernovae for low mass progenitors. This is what you can see here. So the number of supernovae as a function of progenitor mass. I'm only looking at the very low part here of the IMF, but you can see that by extrapolating, you'll have less and less supernovae if you go to more massive stars. But typically we consider that the lowest mass star that can explode as supernova is something like 8 solar masses. Can be a little bit less, can be a little bit more, depending on the sources, but this is typically what people are taking. On the high mass end, people are seeing that actually the very high mass stars probably do not explode as supernovae. They will be failed supernovae and will just collapse as black holes. And it seems to happen at relatively low masses, just above 20 or so stellar masses. This is seen in observations. So you can see here different supernovae progenitors at the function of their initial masses. These are observations, I think all in our Milky Way. Or, yeah, I'm not sure about that actually. But yeah, and you see that we don't see any above 20 or so solar masses. You could think that this is a size of sample effect, right? Because it's only about 19 or 20 supernovae remnants that have been observed here. But actually, what you would expect from the IMF is at least like 3 or so from them would have higher masses. So, okay, if you do actually quite robust statistic on this data, this result is quite robust. There are also theories that support this number. What it means, this is actually very important, that the very high mass stars do not explode as supernovae. Because if you look at the lifetime of the stars as a function of their masses, the highest mass stars live the longest, they live the shortest, sorry. So if you have 100 solar mass stars that explode as supernova, it will do so after just above 3 million years. Now, if we have to cut this, because all these stars just form black holes, it means that the first supernova, if you have a population of stars, the first supernova that will explode will only do so after about 10 million years. And this is not solar masses, this is million years. So the first supernova is typically assumed to be after 3 to 4 mega years. But if you cut this distribution of stars, you actually only explode your first supernova after 10 million years. And this is why I was saying in the previous slide that they don't have really a role in stopping star formation. It's because after 10 million years, you already had radiation pressure, you already had jets, you already had photoelectric heating and ionization. So the gas is gone after this time. So the supernovae are important, we'll see that, but not to get rid of the clouds. And I'm almost there. So we've gone through this list. Now the matter is to put all of this together, right? And I encourage you really to look at the StarForge project, to see this video in high resolution, because it's pretty cool. But okay, it doesn't do too bad of a job here. So you can see the collapse of this cloud that we started with. It's turbulent, so it forms structures. You see filaments and sheets. You see the first stars that are forming here in the very dense part of those filaments. And after some times, we'll see the effect of feedback. Mostly when the most massive stars will start to be formed. We should already see some jets. I don't know if you see them. Not yet. Okay, here, okay, it's a bit faint. Okay, here we have a jet very clearly, right? Here we see some jets. Here, now you really start to see them. So the jet from the more massive stars will start to see some bubbles that are created by the winds. Okay, it stutters a bit. But okay, yeah, I really encourage you to go on here. You see the winds here, very nice bubbles. And if I go forward a bit, because it's a bit long, you see that after some point, okay, the gas is mostly gone right now. And here was a supernova exploding and basically getting rid or ionizing the rest of the gas. But before that, most of the gas was already gone from the initial amount of molecular clouds. Okay, and this is a movie made by Mike Grudich and David Guzmanov. Okay. Okay, maybe I stop here for a few questions, and then I'll go to the impact of GMC scales.
Hi, thanks for the overview. So I wanted to comment on something you said in the beginning, that maybe it was not meant to sound this way, that if there was no feedback, everything would collapse to black hole. So when you actually do a simulation, that's not the case. You can turn off feedback and still not have everything collapse, because there is significant turbulent energy driven by differential rotation of the galaxy. there is much more energy stored
Yeah,
in the
no,
differential rotation than in the feedback mechanisms altogether.
Well,
So
it
that
was
was
it was a bit provocative. Fine.
Yes, so
but okay,
provocation received and answered.
But if you have dense, like the dense structures, if you have virialized clouds or abound clouds, you can't destroy them just by differential rotation.
We were talking about turbulence, right? So if you expect to drive turbulence by these small scale mechanisms, you cannot. You said that turbulence would dissipate in one crossing time if there was no feedback, but the turbulence you were referring to
on large scales,
is not turbulence that we just saw in this video, because you started with they started with a turbulent cloud that was driven on scales comparable to the cloud. That cannot happen from the feedback mechanisms that are shown here.
Yeah. Okay. Good. Thank you. Thanks.
Thank you for your talks. I just wanted to ask if outflows always have to be magnificent, like, in like super large scales, or can they be on shorter scales, occur on shorter scales as well?
Okay, first I have to say I'm really not an outflow specialist, and that is because they are actually on relatively small scales for me, who is looking at GMCs in nearby galaxies. I don't think we see them because they can be long, sure. I think it will depend on the medium in which they expand, right? The density of the medium. But they're not on very large scale, I would say.
No, because yeah, I understand. Okay, because every time we see pictures of galaxies undergoing an outflow, it's always
sure. I think it's probably more impressive when they're longer, but I would say that there is a range depending on the medium. That's what I would say after. But I'm not a specialist on these scales.
All right, thank you so much.
Hi, thanks for your nice talk. So what I wanted to ask is that suppose when the stars first form, like they first form and they accrete mass from the surroundings and grow large, right? And at some point, because of feedback, the accretion stops. So what do you think, like comparing, if we want to compare the effect of radiation pressure and the photoionization, which one has a bigger effect on this?
Between radiation pressure and photoionization?
Yeah, like which has a higher effect on settling the final mass of those stars or on the accretion process?
Okay, the final mass of the stars. I know that I'm going to show that actually. I have a slide about that, about the IMF later. Actually, outflows are important for setting the IMF. But because they're important for the mass of single stars. Now, if you talk about the larger star formation efficiency of a region, then the answer is going to be photoionization. And again, I also have a slide about that, comparing photoionization and radiation pressure.
Okay, thank you.
Yeah.
Thank you for your talk. So I have a little question, either just want some comments. So you mentioned ionizing radiation, and there you had an ideal, let us say, situation. And can you say what effects can suppress it? How, like, I don't know, some metal cooling, whatever, can increase time scale or decrease?
For photoionization?
Yeah, for ionizing radiation. There was a slide on your presentation.
Okay, it's a bit of a mess, yeah. I have to go back. Okay, it definitely depends on the density of the medium. It probably depends a bit on metallicity, but I would say not too much. Yeah, I would say mostly density.
Okay,
and the luminosity of the source. So how much stellar mass you have.
Got it, thank you.
I wanted to ask whether there's a way, I mean, you showed very clearly that in a single cloud, you have multiple feedback channels and maybe a clustered environment.
Mhm.
So is there a specific, a special scenario where you can imagine feedback having the effect of promoting additional star formation in the cloud?
So you mean star formation triggered by feedback?
Yeah.
Yeah, so that's actually a debated question, I think. So some people claim that if you have an expanding shell, either by supernova, for example, or by winds, and then in this shell, you see star formation.
Mhm.
Okay, but the big question is, is this star formation triggered by this expanding shell or by this shock, or would it have happened anyway? And one argument for that is that if you have star formation, it means that you have dense gas. If you have dense gas and if you have a shock reaching this dense gas, because of the high density of the gas, the shock is going to slow down. So the shock is going to spend more time, or you're going to see it proportionally more at this dense gas. So you have this necessary time correlation. So that's why it's not necessarily a direct proof of trigger star formation, I would say, but I think it's debated.
Okay. Thank you.
I don't know if we should continue or
Yeah, let's go ahead
there
and
was
continue.
more questions.
Continue.
Okay, so now that we've reviewed the different feedback mechanisms, I'd like to go about how do they impact the surrounding, and in particular the local surroundings, so the medium. So the heat and the ionize the gas that we've seen. The feedback disrupt the GMCs. It limits star formation efficiency, and it impacts the IMF. So I'll go through each of these points. So we've seen already that the effect of heating, ionizing, and expelling the gas. I just wanted to show you a couple of new images from James Webb. So we've seen that it's in our galaxy. This is pre-James Webb. So you see these bubbles here blown by feedback in the LMC. And what is really nice, and we've seen that this morning and in Danny's talk already, I think, these bubbles blown by feedback are also now seen everywhere in nearby galaxies with James Webb. Now, what about disrupting feedback, disrupting GMCs and limiting star formation? Now it's time to wake up again. So I've put the list of all feedback mechanisms that I've just talked about, and asking you which one do you think is or are, I think you can choose several of them, the dominant feedback mechanisms on GMC scales. I think with what I've said, and especially how I answered the question, you can have a bit of an idea already. I know I haven't talked about cosmic rays. I know. I'll give you 5 more seconds to finalize your answer. All right. I'll stop now. Okay, so it's quite balanced, actually. We have a lot of votes for ionizing radiation, winds, and supernovae. Quite less for radiation pressure. I guess that's because of how I answered that question. Well, okay, I haven't talked about cosmic rays, and I won't talk about them today, but I think they mostly act on larger scales, so not so much on GMC scales, indeed. And outflows, okay, or can be of some importance. So let's see what observations tell us. Oops, so I'll go back to the presentation. So what I want to know is how stellar feedback, or which stellar feedback mechanisms regulate star formation efficiency and star formation on GMC scales. The question that I'm actually really asking is how fast GMCs are dispersed by star formation. We've seen that these different feedback mechanisms can be associated with different timescales, characteristic timescales. So if we know how fast the clouds are dispersed, then we can say, okay, which feedback did it? That's the idea. But that's not necessarily a simpler question, because it's not easy to measure how fast star formation happened. And it was actually in one of the last questions that Julia was asking this morning. What are the timescales of star formation? And many studies have focused on that questions, focusing on nearby galaxies, mostly measuring the number of molecular clouds between galactic arms. And if you assume that star formation is triggered in the spiral arms, you get something like over 100 million years for the lifetime of the molecular clouds. This method is quite simple. The question is whether it actually measures the timeline or the lifetime of molecular clouds or of actually molecules. But it has to make these quite strong assumptions that stars is triggered by spiral arms. And this is not necessarily true. So other techniques have been developed to, again, measure the lifetime of molecular clouds by classifying clouds. So basically you count in a galaxy how many of clouds don't have stars, how many of clouds have some stars, and how many of clouds are already like partially destroyed by feedback. Knowing how many of clouds you have in each categories, you know how long they spend in each of these categories. So again, it's a relatively simple and straightforward method, but it's quite subjective. You have to put clouds in a category. That's always problematic. I know we do that a lot in astronomy, but yeah, it's very subjective. And it also requires to resolve the clouds. So you can also only apply that to a limited number of galaxies. And other studies, again, have been focusing clouds along a stream of gas in the center of our galaxy. And here they measure something like 1 megayear for the lifetime of the clouds. The problem here is that you have very small number statistics. Basically, this was only done in the center of our galaxy. So very small regions, just a few clouds. You have to assume that the star formation was actually instigated at one given point around this orbit, and then you follow the evolution of the cloud. So it's very difficult to expand to other cases. And so it was unclear whether these 2 orders of magnitude here between 1 and 100 of million years for the cloud lifetime is physical, because just very different environment, or if it comes from differences in the experiment design. So what I want to show you in the next few slides is a method to actually measure the lifetime of the clouds. So how long it takes for the clouds to form stars and how long it takes for them to be destroyed by feedback in a quite objective and systematic way. And for that, to illustrate that, I want to come back to a very, very simple question in a way. The question that we want to answer is, do clouds live for much longer than massive stars or for similar timescale? In other words, do we have a quasi-equilibrium between gas and stars, or do we have a rapid cycling where clouds are destroyed as soon as they form massive stars? What you would see observationally is that gas and young stars here are correlated on small scales, but here they decorrelate on the small scale. You either see gas or you see stars, but not both at the same time. Now that we have really high resolution of nearby galaxies, we can actually check that very quickly. So this is a nearby galaxy, NGC 300, and in red, you see the H2 regions, so basically young stars. And in blue, you see the molecular gas. And I think it's pretty straightforward to see that you have these young stars that have no gas associated with them, and you have these molecular clouds that don't have stars associated with them. So you have a spatial decorrelation of gas and stars on small scales. It means that we're in the case of the rapid cycling. And then the question is, how do we quantify this rapid cycling? Can we actually measure this time scale? And the answer is yes. So you can do that by measuring the gas to stellar flux ratio. So basically, yeah, blue divided by red here, the gas to stellar flux ratio on different size scales in the galaxy. So if you measure for the entire galaxy, well, you have the galactic average. But now if you just measure this gas to stellar flux ratio around these blue peaks, you have an elevated gas to stellar flux ratio. If you do the same thing for the red peaks, then you have a depletion of the gas, so a low gas to stellar flux ratio. And you can do that at different size scales. And this discrepancy here, when you focus on the gas or when you focus on the stars, it directly traces the spatial decorrelation that you see in the image. And that characteristic shape here, you can fit with an analytical function that depends on only 3 parameters, which are how long the clouds live, how long stars and gas are correlated together, basically how long the feedback phase lasts, and how far apart these different regions are in the galaxy. So you can just fit this analytical function here. I'm not going to give the expression because it's a bit, it's not difficult, but it's a bit cumbersome. And you can fit this for an observed galaxy. So this is what we've done here. So again, this same galaxy, we have measured the gas to stellar flux ratio, focusing on the molecular gas peaks for different aperture sizes, focusing on ionized gas peaks, so young stars for different aperture sizes. And we fitted these 2 branches here. These are the dotted lines. And the best fit here is for 11 megayears, so for the lifetime of the clouds. It's actually quite short if you compare to this 1 to 100 megayear range that we had before. It's really close to the freefall time of this cloud. So it suggests that the clouds, when they're formed, just collapse and start forming stars. The feedback timescales is also pretty short, 1.5 megayears. If you remember the delay time of the supernova, it was at least 3 megayears, but more likely 10 million years. So this is clearly, the clouds are destroyed before the supernovae can explode. And the last bit of this timescale here is where you see only the stars, so only H alpha in this case. We use that as kind of a reference timescales to calibrate the rest of the timeline. And was not going to mention that, but because there was a question about that, I think last week on Tuesday, during Benjamin's talk, and I think that was also discussed this morning. I don't remember in which of your talk. Yes, in Danny's talk. Actually knowing how long you see H alpha and how long you see FUV radiation are quite of important questions. And it's also, I want to mention that when we use H alpha to trace star formation, we always trace past star formation, right? I think it's important to keep in mind, because you'll have H alpha that is emitted for a certain amount of time. So here we just consider a simple burst of star formation, like here. But then you'd still see H alpha for a long time. And after that, you have a steep decline. But you see that for FUV, it's not as steep. You see FUV for a much longer time scale than H alpha. And this is what Danny explained this morning to explain the shape here of this curve. And yeah, talking about tracing past star formation. So yes, if you use H alpha, you probably trace star formation that happened between 0 and 10 million years ago, on average 3 million years ago. But if you use FUV or NUV, you can see that this range actually extends. So you don't really only trace only current star formation, but really past and average star formation. And you can calibrate this timescale a little bit more in detail than this range is here, using the method that I've just described for different filters of here it's Galaxies, Swift, and HST UV filters. And you see that the characteristic timescale that you, so what actually timescale do you trace using different wavelengths is actually, actually depends a lot on what wavelengths you're using to trace star formation. So that was just a little side note on star formation tracers. So to go back here, so how do massive stars impact their surrounding? How do they in particular disrupt GMCs and limit star formation efficiency? Well, we can test that in nearby galaxies. So the method I've just explained earlier to measure how long clouds are living and how fast they're being destroyed by feedback, we have applied to all of the FANG's galaxies. And you can see this characteristic shape, this characteristic tuning fork shape here with this decorrelation at small scales, meaning that you have a rapid cycling between cold gas and young stars. Cold gas and young stars are never very long together. And this means that you can constrain this timeline for all of these galaxies and measure the cloud lifetimes. So between 5 and 30 million years, it depends on the galaxy, it depends on the environment. But I'm not going to focus about that today. Of course, I want to talk about feedback. So you can see that for all of these galaxies, the feedback, so the cloud destruction phase is quite rapid, between 1 and 5 million years. And this is also what you see if you look precisely on individual clusters in galaxies. So you see these examples here of embedded stars, of embedded clusters, partially embedded clusters, and exposed clusters, where H alpha is in green. So you can really see here the bubble, sort of the shell of H alpha outside of the cluster. So if you do that, if you look at individual clusters, you see that young clusters are actually gas-free after 3 to 5 million years. So this is consistent with what I was showing before. The problem here is that you really need to look at pretty much individual clusters. You need to resolve and age date the young clusters. So you can only do that in a limited sample of clusters and of galaxies. It's quite challenging. But yeah, these two methods basically give the same results. Molecular clouds are disrupted between just a few, within just a few million years, so before the first supernovae. This timescale is environmentally dependent. So if you look at the cloud destruction time as a function of the surface density contrast, so whether clouds are embedded in a dense medium or clouds are kind of isolated in a diffuse medium, well, you can see that here they survive longer. It's much more difficult to destroy these clouds than when they're isolated and then you can just push the gas away in a diffuse medium. Because they're destroyed very quickly, it means that you cannot accrete a lot of gas, right? You start forming stars and then the gas is, the molecular gas is destroyed. So that drastically limits the star formation efficiency. And this is seen in simulations. You can see here the star formation efficiency for typical clouds that are observed in nearby galaxies is just a few %, right? So a few % of the GMC is going to go into stars, and after that, most of the gas is gone. What is interesting is this dependence here with gas surface density that is seen in simulation. And there is also in in observations, we see dependency here of the star formation efficiency with the star formation efficiency with the star formation rate surface density. And the fact that we have this early pre-supernova feedback is quite important, actually, because it pre-processes the medium before the first supernova can explode. And this has been measured quite in detail in this Galaxy GC300 by MacLeod et al., where the pre-shock ISM density of supernovae remnant, you can see is pretty low. It's just below 10 particle per cubic centimeters. This was also seen in nearby galaxies, so of the FANGS survey, where supernovae remnants are indicated here as this white dot or so, and they rarely correspond to the CO peak. So if you remember the simulation images I showed at the beginning, yes, simulations don't do much when they're embedded in a dense medium. What we see is that they are not typically embedded in a dense medium because this medium has been processed already by pre-supernova feedback, so they can have an impact on much larger scales. So now it's the time to go to the time scale, to compare the time scales that I was deriving at the beginning. So which one actually of this time scale limit the star formation efficiency? And what feedback mechanism can disperse the gas so quickly? So we've kind of ruled out already jet and outflows because they disperse cores and not GMCs. I'm showing here supernovae, but from what I've said, they're kind of excluded as well. But okay, well, we're still going to consider them now. But we're left with ionizing radiation, stellar winds, and radiation pressures. And these are the equations, same equations that in the first part. So you can basically compute here these equations, replacing the density and the luminosity of the sources, etc., and calculate for each of them their characteristic timescale. And here I'm showing it as a function of galactocentric radius in the Galaxy GC300 that I've shown already. So this is just one example for one galaxy. You see that, okay, supernova, here we've just taken 3 million years. So this is really a strong lower limit. Said it that you typically, probably supernovae, we could have put that line over there. Radiation pressure, for that galaxy at least, if you compute this equation, you find relatively long time scales, right? To actually destroy the clouds, you need, just with radiation pressure, you need to wait for a long time. But for photoionization and stellar winds for the ideal case, I have to say, you find similar timescales of about 1.5 to 2 million years. And this is very consistent with the data points here of how fast the clouds are destroyed in this galaxy. So yeah, photoionization and stellar winds are very good candidates to what is limiting star formation efficiency in these galaxies, in this galaxy. Now I can do the same exercise for more galaxies. So I'm going to show that a little bit differently by showing here the predicted feedback timescale for different mechanisms and the observed, as a function of the observed cloud dispersal time here on the x-axis. And there is a one-to-one relation here. So if the data points for given mechanisms fall above the line, it means that the mechanism is too slow. Its timescale is longer than what we observe. And if it's below the line, it's fast enough. So for supernovae, as you might have expected, for here about 10 galaxies, almost all of the data points fall above the line. Even if you still consider that the most massive stars can explode as supernova within 3 to 4 million years. Now the data points for a combination of winds, photoionization, and radiation pressure, they're below the line. So the predicted feedback timescale is fast enough is actually faster, much faster than what we've observed. And the conclusion that you can draw from that is that, so yes, pre-supernova mechanism is important, but the coupling efficiency with the gas is not 100%, right? Because, yeah, these could destroy the clouds actually faster than what we see. And this is seen in simulations where you can see that just for the single clouds here, because of the medium is not homogeneous, you have low density channels where photons and energy can escape and not interact and not destroy the gas. Okay. So let's compare this with some simulations. So there was a question earlier whether ionizing radiation or radiation pressure was more important in stopping star formation or limiting star formation efficiency. So the simulation here by Kim and a Stryker showed that the star formation efficiency as a function of the gas surface density. So it increases with gas surface density. You can see that it starts pretty low, right? So again, just a few percent to maybe, okay, 15% or so of star formation efficiency. If you just add radiation pressure, it's these blue dots here. So you can see that it doesn't limit too much star formation. Ionizing radiation alone does much more, limits much more star formation efficiency. And if you add both, it's actually not very different. So yes, so ionizing radiation is very important for limiting star formation. Note, by the way, that if you don't add any feedback, you're somewhere here, right? So at over 80%. So yeah, adding feedback really, early feedback really stops or limits the star formation. Okay. Sorry, up. Now this is for this very complete simulation. So for the Starforge simulation, the movie I was showing earlier, this is basically giving sort of the same result. So the star formation efficiency is here. Now it's as a function of time. So what you want to look at is how much star formation efficiency you reach at the end of the simulation. So when the gas is gone, you see that without any feedback, you're somewhere here and it doesn't stop. So maybe it goes even further. But if you add all the feedback mechanisms, and in particular, stellar radiation and winds, you're here. So just a few, again, just a few percent. And again, this is, you can see that the turnover happens way before the first supernova explodes. Right, so when the first supernovae are not really helping in limiting the star formation efficiency, this is done before. And just to say one word about magnetic field, because it might be important, but I think we don't have really observations, too much observations about that yet. But simulations can show that. So here again, it's star formation efficiency as a function of magnetic field. So more magnetic fields are here, more magnetic clouds are here, and less magnetic clouds are here. Star formation efficiency doesn't care too much, it seems, about the magnetic field if you're at low magnetic fields. But if you look at clouds that are subcritically magnetic, then there is a drastic change. There is really a big effect in star formation and in the limitation of star formation efficiency when you go to more magnetized clouds. Okay, so after simulations, we can also look at observations and compare whether radiation pressure or photoionization dominates or limit the star formation efficiency. What is shown by several studies is that the dominant feedback mechanism really depends on the evolutionary stage. So when you're looking at a region, if you're looking at young H2 regions, radiation pressure dominates, and that makes sense in the context of what I said, that you need an optically thick medium to care about radiation pressure. So when the regions are still young and compact, then radiation pressure is dependent. But when you look at older, more evolved regions that have already expanded, then the importance of radiation pressure drops, and photoionization pressure will dominate. Yeah, so this is seen in the LMC and SMC, and this is also seen in further away galaxies. But here we're limited by the resolution, right? So yeah, this was for more evolved regions already, so the photoionization pressure dominates over the radiation pressure. Now, how does it depend on environment? This is not an easy question to answer because you need this very high resolution. So this is a study that was done by Feng. So again, showing the the pressure as a function of the radius of the region. So the purple data come from the plot from the previous slide, the purple and the orange data. And the Feng's data are these contours here. And you see that the thermal pressure dominates over the radiation pressure for these regions, but you can see that they're quite evolved already. So they're mostly unresolved H2 regions. So I think we're waiting for JWST data here to really probe the heated dust pressure in these nearby galaxies. I'm not sure I have time. How much time does I have still? Okay, then I'll skip. Okay. Okay, maybe I do that quickly. You might have noticed that the cloud lifetime I said was relatively short, but this orange part of the timeline, so where you just have clouds but no stars, is quite extended. It's 70 to 80% of the clouds. And one of the questions is whether actually clouds are really inert during this phase. And actually this is linked of a question that somebody asked: when do you start seeing H alpha? After what time after star formation starts do you start seeing H alpha observations? And this, I think, is a very good question, because we know that star formation is, H alpha is extincted for very embedded young stellar regions, but they can be seen in infrared before being seen in H alpha. So you can apply exactly the same method as I described before, but this time not using CO and H alpha, but using 24 micron emission or any far infrared tracer. And if you do that, you have these timelines that you see here, and you see that for almost all galaxies, you start seeing 24 microns, so far infrared emission, a little bit before H alpha, between 1 and 3 million years. And that was before James Webb. Now with James Webb, we have many more galaxies. And basically, I'll go directly here, but it's the same result. Deeply embedded stars, so invisible in H alpha, last for about maximum 3 million years. So you have star formation that is initiated in a cloud. You don't see H alpha for between 0 and 3 million years, and after that you do see H alpha. So this phase is actually quite short. In some galaxies it might be pretty fast, so the embedded phase might be pretty short, but in any case, after about 3 million years, you definitely see H alpha. Yeah, so I'll go here immediately. So I said before that if you calculate the expected timescale for the feedback to disrupt the clouds, it was actually faster than what you see. So the coupling efficiency is not 1, or in other words, the escape fraction is not 0. You have photons that escape the medium without participating in destroying the clouds. And this is, seen in simulations, that you have pretty high escape fraction of a few tenths of percent, about 50% or so. In observations, we see that too. It's very difficult to make the actually quantitative comparison, but I think qualitatively, we agree that the escape fraction is pretty high. And it means that a large fraction of the energy can actually be used to the, on larger scales. And that might explain, at least partially, why we see diffuse ionized hydrogen emission throughout galaxies, and not only just locally in H2 regions. Okay, there is a slight dependence, it seems, of this coupling efficiency, or 1 minus the escape fraction here as a function of metallicity. So you expect low metallicity galaxies to have a more porous environment. So the escape fraction is higher, or the coupling efficiency is lower when you go to low metallicity environment. I'll skip the other plot. Last word about the impact on the IMF that we've heard already from Steffi last week. Protostellar jets are important for reducing how much mass you can accrete on a star, because it directly removes the accreted material and it disrupts the accretion flow around stars. And this is again from the Starforge simulation. So many different lines, but basically the green line here is without feedback. It's just the base here. You see that you get you get close to the Krupa IMF when you start to add protostellar jets. Just thermodynamic doesn't make it. But if you start adding protostellar jets, it's this purple line here, and you get that Krupa IMF. If you add all of the other feedback mechanisms, but not the jets, you get these yellow lines here. So not enough low mass stars, but too many high mass stars. So jets are very important for that. So last questions in the few minutes that I have left. What do you think now about the dominant feedback mechanisms on galactic scales? Is this? Sorry, I think it's lagging here. Do that here. Yeah. So we've seen on small scales that outflows are important for the IMF. The rest, ionizing radiation, winds are very important for setting the star formation efficiency. Radiation pressure is not too important for that. Supernovae arrive too late. So this was on the small scales. Now, what about the large scales? Five more seconds. Okay. Stop here. Okay. Yeah, so supernovae, cosmic rays are probably the most important mechanisms on large scales. These might have an effect as well. We've seen that there was an escape fraction that was quite large, so you might see a little bit of an effect, but yeah, these two are probably dominant. So this is what I'm telling you, but you don't have to believe me. Actually, can we prove or can we see that that these small-scale feedback mechanisms affect the large-scale medium? Or do we care? If I'm working on galaxy evolution, or if I'm a cosmologist, should I care about everything I've said in this talk? Well, actually, yes, it's very important. So this has been shown already for several years, but this is a quite recent simulation that different feedback mechanisms on the small scales, on just the scale of a few parsec or a few tenths of parsec, choosing different feedback mechanism changing completely the appearance and the morphology, the properties of the simulated galaxies. And even for one single mechanism, I'm just talking about supernovae here, the details of this mechanism, here the delay time, changes completely again this the appearance of the galaxy. And we've seen that this was kind of not entirely clear when the supernovae explode. So yeah, these details, these small scale details actually matter a lot on large scale. So yes, we care. On galactic scales, so what does feedback do? It limits, because on small scales, it limits star formation efficiency. It will regulate the star formation rate on large scales. We've just seen it can change the morphology of the galaxy, and it regulates galactic outflows. And I don't know if I have time to talk about that. But this I want to mention because it's important. How does the small scale feedback regulate star formation rate at large in galaxies? So you probably know that there is kind of a discrepancy between the depletion time that we observe in galaxy on scale of a giga-year typically, but we know that star formation happens on, or the clouds collapse on just, you know, the free fall time of a cloud is a few tens of million years. So how do we reconcile this? This is the self-regulated star formation model. So it's a way of understanding this discrepancy. You can assume that the galactic disk is a system in equilibrium, where basically the sum of turbulent, thermal, magnetic, pressure balance the weight of the ISM. And over this list, turbulent pressure and thermal pressure will matter the most. So it means that turbulence dissipation and radiation cooling must be compensated. So, okay, maybe not as much as I was saying at the beginning, but still. And star formation is a way, so by supernovae and photoionization and photoelectric heating is a source of energy and momentum. So it will sustain turbulence and heat the gas again. This is, so it will prevent collapse. I'm gonna skip over that. So what you need is a local star formation to keep this long-term equilibrium. You need a star formation rate that will sustain the weight of the ISM. So this is, you can calculate that as a dynamical equilibrium pressure that I'm going to call PDE in the next slide. And the ratio between PDE and the star formation rate surface density, we call the feedback yield. Okay. So what simulations shows is that indeed, if you calculate this PDE pressure here as the sum of all of these terms here that are basically the scale with star formation, you can compensate here the weight of the ISM, right? You have this nice linear relation here. And even more, so if you look directly at the star formation rate surface density as a function of this, this pressure that is imposed by the star formation rate, you get this, you can sustain this equilibrium of the ISM. You can also, so this is from simulations, you can also see that in observations. So this is the same plot. star formation rate and the pressure, which is the sum of the thermal pressure and the turbulent pressure here. And you see again this nice quasi-linear correlation as for the simulation. And I don't have much time anymore. Okay. So just then last point. Yeah. So simulating feedback is not easy because it involves a large amount of different scales, right? We know that star formation happens in cosmological context. So you need to zoom in, like if you want to take into account the accretion of gas onto galaxies, a galaxy, the star forming regions within this galaxy, down to the formation of single stars and their and its protoplanetary disks, then it's 12 orders of magnitude that you need to cover in space. And it's not only that, but also, again, if you want to simulate galaxy formation and evolution, but also take into account the detailed effect of supernovae, it's here 9 orders of magnitude in time that you need to cover. So computationally, taking into account all of these scales, really modeling star formation and feedback, how star formation and feedback affect galaxy evolution from first physical principles is computationally impossible. So what you do is that you cut up that a part of this scale, and you need to assume like sub-resolution prescriptions for what happened at the scales that you can't resolve. And the way of doing that is either you tune the many free parameters of your sub-resolution prescriptions until you get what you expect from observations, or you use directly the result from small-scale simulations. Or a third approach is to use empirical results from observations and plug that in your simulations. So this is kind of a new approach that we can now use because we have constraints. We are just starting to have constraints from observations on the feedback and star formation mechanisms, but this is not something that is very common. I don't think I have much time to go through that, but I just wanted to show you a very quick comparison between a supernova only case for simulation or a case where we've plugged in the results from the observation. So how fast feedback destroy the clouds from observations. So there is not much physics, but it's really empirically driven. And what you see is that the galaxies here, the simulated galaxies, look completely different. Especially, you have much smoother disk here if you have this empirically motivated feedback with early feedback compared to supernovae only, where you have very clumpy stellar distribution with very massive clusters. This means here that because the stars are very clustered, the supernovae are going to be very clustered. And the effect of that is that the outflows or the galactic winds that are ejected by these two simulations are very different. You have about an order of magnitude here different for the gas outflow rate if you just have supernovae that explode in a cluster way and can really launch a lot of gas out of the galaxy, or if you have early feedback and then the supernovae also happens, but later on, less clustered, and then the outflow that are launched are much less powerful. So this is important. You see, this small scale effect of feedback is important also for cosmological scales. So that's just a summary. I have one last very important, probably the most difficult question for you to see if you paid attention. If I can launch it. what is stellar feedback. And I'm not going to read that. I have to say I did not come up with it, but contrary to Benjamin's talk, which was not made by ChatGPT, this slide was made by ChatGPT, I have to admit. Okay, well, I can let everybody reply. But then, yeah, now so thank you for listening, and I'm happy to take your questions now.
Thank you for a great talk. What is the way to observe feedback in galactic scale? It seems like most of the feedbacks like work right now in galactic scale are done in the simulation. But
Are what, sorry?
most of the feedback like in galactic scale seems to be done in the simulation. Like how can we observationally confirm that it happens?
Yeah, so yeah, that's a great question. I think indirectly we can probably see, so with galactic winds, for example, also go probably cosmic rays observations, which I'm not too familiar about, but these are typically at low resolution. This is why I did not mention them here. But then if you're interested at larger scale, then they can probably be used to constrain, yeah, what is the influence of cosmic rays on larger scales. Yeah, I would say these are the two ideas that I have right now.
Yeah, so I have another question regarding this empirical feedback implementation. What is the difference between having this empirical calibration and having a statistical calibration, as is done regularly with like the Schmidt-Kennicott law? What can we learn that is different from this sort of calibration?
Well, the Schmidt-Kennicott relation doesn't give you the feedback, right?
So you give me the star formation rate, but what is
yeah.
different in what
Well,
you have implemented that teaches us something about the
here
feedback process?
both galaxies follow the Schmidt. It's also a constraint for both simulations here is that they do follow the Schmidt-Kennicott relation. They form pretty much the same amount of stars. This is what I find quite striking, is that they form the same amount of stars, but not in the same place. And then they look completely different.
Could you explain what was different about these two?
So yes, this is kind of the slide I skipped. In the supernova only case, you input basically momentum very, very suddenly. So after like 3.5 million years, you have feedback from supernovae. In this case here, so there are two flavors basically of the simulation, but the results are almost the same, is that you have a specific terminal momentum that you reach that is set by the observations. And before that, you input feedback in the cells next to sync particles. You input a momentum following self-similarity here from when you start forming stars, not after 3 megayears, from the star formation. All of this time, you input a little bit of feedback or momentum instead of doing it late.
Until it reaches this P of T feedback. That is empirical.
And until it reaches this.
So that is the quantity that is empirical.
After about 3 million years. Yes.
Okay, thank you.
So when measuring the like correlation and spatial decorrelation between massive stars and gas,
Mhm.
of course, feedback is one of the dominant effects that causes them
Yeah.
to not be
Yes.
spatially correlated. However, how would you take into account the fact that stars are also just dispersing away from molecular clouds, and from what I can tell, on similar timescales?
So yeah, you can imagine that stars and the clouds are just displacing. That's sort of what you're asking? If you make that calculation for the clouds that we're looking at here that are pretty big, you will need to move away the stars really fast, all of them in one direction, like from the gas. And these are actually speeds. I don't remember the exact number, but several tens of kilometers per second. And it's actually, yeah, that's too fast to be realistic. Yeah, but all the stars would need to be run away in that case, right? Because it's the bulk. It's not just a few stars. We're talking about associations of 10 to the 2, 10 to the 3 solar masses, not single stars. So then, yeah, that's not too likely, I would say.
Hey, great talk, thanks. You probably are know about the recent result from RCW 120, so where they obtained C plus data and concluded that the time scale of the expansion of the stellar feedback was very, very high. So it was almost 15 times what was previously thought. And they also said that it was highly unlikely that the cloud was already full of clumps that could collapse to form stars. So based on these two conclusions, they concluded that there was probably triggered star formation. So what do you think of such a scenario, and yeah?
I haven't seen that specific result, I have to say, so I would need to look at that in more detail. Yeah, but for now, yeah, I can't add more than what I said before. I will look into it. Thanks.
Thanks for the talk. I have a question about star formation efficiency, actually. So, of course, stellar feedback is not the only factor that affects star formation efficiency, right? So, do you have any comment on how dominant it is, and like to what extent star formation, stellar feedback has on star formation efficiency?
You mean locally on the scale of a cloud?
Yeah, and also what scale? So you're talking mostly about cloud scale, right? But also in galactic scale, the structure, like clouds in different structures in galaxy also have different star formation efficiency.
Right. Okay. Well, yeah. I mean, I've shown both observations and simulations show that star formation efficiency is dependent on the environment. So if you start with a cloud that is more or less massive, more or less dense, you will have a final star formation efficiency for that cloud that is different. I'm sure there is also a role of metallicity. Observationally, it's still difficult to prove that. In simulations, I think this is seen as well. So yeah, it's environmentally dependent. There are also effects like in spatial environments, like we've mentioned this morning, the central molecular zone. There you have shear that prevents the clouds to collapse. So that's another parameter, but that's again, that I think that's a very special environment. I wouldn't expect that in the disks. I think there it's mostly feedback that limits star formation efficiency.
Thank you.
Other questions?
So why do we still see molecular gas in the interarm or in the disk if it's so short lived?
Yeah, so the time scale that I'm mentioning are for the lifetime of molecular clouds. I'm not talking about the molecular or the molecules themselves. And I do think that there is a large reservoir of diffuse molecular gas. We see that in between the arms or yeah, in galaxies in general, right? So yeah, I don't think the effect, and this is actually a question that what is the feedback doing? Is it actually destroying the molecules or just making the gas less dense so that we don't see it as molecular gas anymore? And I think this is mostly the second point. And this is why then it's relatively fast to form again clouds, because you don't need to form the molecules. That would take a long time. You just need to reassemble, collect them.
Melanie, one question I have with the radiation pressure is that for most of the continuum IR, as you say, at the optical depth, not enough trapped ones, but then you've got specifically emission lines that can be trapped multiple times, and especially Lyman alpha, which bounces back and forth multiple times and can add quite a bit of radiation pressure. I'm curious, what do you think the relevance of that term is?
I suppose this is included in the simulations that were taken into account not well. Okay. Right. Yeah. So, okay, maybe that would help a bit radiation pressure to have some effect. As you could see, like it was way slower than winds or photoionization. So I think even if you increase its efficiency a bit, I'm not sure that would be enough though still. Yeah. And as you start dispersing the gas, it will become less and less efficient. So maybe it helps at the beginning and then quite fast it will be overtaken.
Could you go to slide 26, please? Is that possible?
Yes.
Yeah.
This one.
Yeah, you said that, there's a difference in those three figures with the right one being clustered. So how does that rightmost one that's clustered, how does that compare to observations? Was that comparison done? Do you know?
I'm not sure these scenarios are very realistic. I showed them for the, for the comparison between themselves, but okay, totally random supernovae are not realistic, right? They're going to happen in specific places. Here, they've selected a fraction of supernovae, like a certain fraction of them that are going to be clustered. I think it's quite ad hoc. Yeah, so it was more for the comparison. I'm not sure it's really realistic.
Other questions?
Behind.
Thank you for the lecture. I just wanted to clarify. I think I understood the relative when you count how much clouds don't have stars and how many have. I think I understand the relative fraction of that, but from the relative to the absolute lifetime, I'm a little bit confused still.
Yeah, great question. This is basically why you need to know how long H alpha would be visible for, because yeah, exactly. You said it, you have relative lifetime, right? So you know how long clouds are living relatively to how long stars are living, very schematically. If you know how long H alpha is visible for, you can, you can calculate the absolute timescale. So this is why I was in the previous slide calling this time the reference timescale. This is what we're using for the lifetime of H alpha. Basically, here, at this transition here, you stop forming stars because by definition, you don't have gas anymore. So the last star that you can form schematically is here. And then this star, this massive star, if you form a massive star there, it can emit H alpha for another 4 megayears. Like, yeah, schematically, this is what is happening. And then so you can use this reference timescale to calibrate your timescale. And okay, now I'm talking about single stars. Of course, this is for a population of stars. And so we've calibrated that using stellar synthesis population models. So that's how you get this 4.3 here.
I have a question related to the lifetime of the cloud before feedback kicks in. So you said, that lifetime is close to freefall time.
Yeah.
So does it mean that if a cloud is doomed to form stars, then it's basically collapsing the whole time? And isn't it like in contrast with what we saw earlier today on the Vira parameter for these clouds?
I mean, it doesn't mean that the entire cloud is collapsing, because as indeed that we can see that from observations, most clouds, at least at these scales, are not bound. So I don't think the entire cloud is collapsing, but yeah, you do find this relation where, you know, at least the internal part of the clouds will collapse, form stars, and get destroyed fast. It's close to the freefall time. Normally, I have a plot. It's between 1 and 3 times the freefall time. So it's not exactly 1 time the freefall time. Yeah, so it's probably related to that. So no, I don't think the entire cloud is collapsing
right
within a freefall time.
Thanks.